Hello and welcome. This is Columbia Basin Research's second video in a multi-part series on using Program SURPH. Program SURPH is a program created by Columbia Basin Research at the University of Washington School of Aquatic and Fishery Sciences. Program SURPH, Survival Under Proportional Hazards, was developed to analyze data from release-recapture studies of animal populations. In particular, to relate the survival estimates from release-recapture studies to individual-based and group-based covariates. Today in the second video, I'm going to show you how to load in your data and create your models. Future videos in this series will demonstrate estimating results as well as various hints and tips on getting the most out of the program. Alright, so at initial startup, no dataset loaded. The load data action on the navigation panel is the only action available. Double clicking on it will bring up a dialog asking the user to select the SURPH input data file. The SURPH format of the input data file can be seen here with the SURPH3 keyword, which must be by itself on the first non-comment line of the data file, followed by a one-line description required. The number of populations indicated by the keyword npop required. The number of intervals indicated by the keyword nint required. A group covariate declaration followed by its name, middle in this case, and then followed by the values for the group covariate. The group covariate values must be numbers, and there can be either one value per population, in which case the same value is used for all intervals of a population, or one value per population per interval. All values for the first population are listed first from the first interval to the last, followed by the values for the second population, and so on. A second group covariate declaration for the group covariate named late. An individual covariate declaration for the individual covariate length. The values for the individual covariates follow the capture histories. In this example here, the first individual of the population, early 1, has a length of 118. The population declaration is followed by all capture histories for the population. A new population is declared with another line with the population keyword followed by the name. The capture histories can begin with an optional tag ID as shown. If the first field is not a 0 or a 1, it is assumed to be a tag ID. If there are individual covariates, the covariate values for the current individual follow the capture history in the order that they were declared. The user is asked to enter the name of the dataset defaulting to the name of the input data file. Once loaded, the dataset names appear under Available Datasets with a green check mark indicating that it is the current dataset. More than one dataset can be loaded at a time. By default, the last dataset loaded is the current dataset. The user may change the current dataset by double-clicking on its name. Hence, you can see the navigation panel with multiple datasets loaded and the one named distance selected as the current dataset. When a dataset is selected, the dataset summary window is updated to show the name of the dataset, its description, the number of populations and intervals, and the number tagged in each population as shown here. There are four main sections under the data header in the navigation panel. It's hard to see, so I'll just minimize some of the drop-downs here. Number 1, data diagnostics. Number 2, manly par estimates, which lacks further drop-down menus. Number 3, CJS estimates, and number 4, CJS profile likelihoods. Under data diagnostics, SURPH provides an M-array report that summarizes the data, 3 Burnham tests and the test model assumptions for release recapture data, and an individual covariate graph for datasets with individual covariate data. Double-clicking on M-array on the navigation panel will bring up the M-array report with an M-array for each population, as seen here. The M-array is taken from Burnham et al. 1987 and gives a summary of the release recaptured data. For population 1, here as an example, 1,467 tagged individuals were released initially. 422 of these were next detected at occasion 1, 211 of which were removed, also called censoring. 201 of the 1,467 were next detected at occasion 2, with 76 of them being removed. 719 of the 1,467 were never detected again. The Burnham tests 1, 2, and 3 are taken from Burnham et al. 1987. Burnham test 1 compares survival parameters across populations, and Burnham test 2 and 3 test for violation of model assumptions. Each Burnham test consists of a series of contingency tables with an associated chi-squared statistic and p-value. 2 tables from a Burnham test 1 are shown here. Their structure and content are specific to each test and are explained in detail in Burnham et al. 1987. At the bottom of each test report is a summary table showing the chi-squared values for each test and the associated p-values. Here you can see the summary table for the Burnham test 1. The overall chi-squared is 31.88 with a p-value of 0.00. Burnham test 1 compares 2 populations, one identified as a treatment group and the other identified as the control group. It tests HO, or the null hypothesis. All survival and detection parameters are the same across treatments versus HA, or the alternative hypothesis. At least some parameters differ between or among groups, as shown here. There are controls at the top of the report allowing the user to select the treatment population and the control population. Burnham tests 2 and 3 look at one population and test for the violation of model assumptions. Both reports have a control at the top to allow the user to select the population of interest, as shown here. Worm tests 2 and 3 are not available if there are less than 3 detection sites after an initial release event. The test specifics are: Test 2, test for goodness of fit of the model to the data. The null hypothesis, the survival and detection parameters are specific to sampling occasions within each group. The alternative hypothesis, the model does not fit the data. There may be tagging effects or differential behavior. Test 3, test for parameters that are specific to individual capture histories. The null hypothesis, the survival and detection parameters do not depend on the capture histories of fish released on any release occasion. The alternative hypothesis, some of the parameters are dependent on the capture histories of fish in a given release. If the active dataset includes one or more individual covariates, SURPH3 allows users to explore the individual covariate data. If we double-click on the individual covariate graph, we can see the individual covariate plot for a dataset with at least 2 individual covariates, length and weight. Under the data selector selection at the lower left of the plot, the user has selected length under the covariate selector, causing a histogram and cumulative distribution function (CDF) plots to be shown for the individual covariate length. Under statistics, the mean and standard deviation (STD period, DEV period) of the selected covariate length are shown for the selected population. Individual covariate weight is selected for covariate 2, and thus the correlation between length and weight is shown for the selected populations and interval. The high correlation between the 2 individual covariates suggests that for creating models that include individual covariate data, the weight may not add much information to the model that already includes length. There are 2 CDF plots displayed for a given individual covariate. Individuals known alive, green, and those not known alive, red. The KS test section refers to the Kolmogorov-Smirnov KS test, Conover 1980, for comparing 2 probability distributions. 2 distributions being compared are: number 1, those known to be alive for the given population period, and number 2, those not known to be alive, for example, not detected at the period or later, for the chosen covariate length in this case. A significant p-value suggests the 2 distributions are not from the same population, indicating that the chosen covariate may have a significant effect on survival and/or detection. Under the heading Graph Options, there are checkboxes allowing the user to hide the histogram and/or CDF. The Manley Parr reports display the Manley Parr estimates of detection probability. Developed by Manley and Parr, 1968, they provide estimates of the detection probability that are independent of the survival process. These estimates may guide the user in selecting the appropriate detection-only model in the modeling process, which we'll go over in a future video. Here we can see an example of the Manley Parr report. The final table, estimates adjusted for removal, are unbiased. Details of the Manley Parr estimates are given in Appendix B.3 of the user manual. The Cormack-Jolly-Sieber CJS estimates, Cormack 1964, Jolly 1965, Sieber 1965, are the best estimates of the survival-related parameters for the release-recapture data. They are described in detail in Appendix B.1.6. Here we can see the report that is brought up in the workspace when the user double-clicks on the CJS estimates, showing the CJS estimates for the current dataset. In this case, there are 10 populations in 3 intervals. S1 is the survival estimate for the first interval, P1 corresponding detection probability for the first sampling event. Final product is the product of survival and capture probability for the third and final interval, lambda, in Appendix B.1.6. The overall S is the overall survival probability, in this case, the product of S1 and S2. Selecting covariance matrix or correlation matrix brings up the covariance matrix or the correlation matrix corresponding to the CJS estimates, as shown here. The report shows one matrix for each population. The CJS estimates provide point estimates for the survival-related parameters. From the standard errors provided, one can construct a confidence interval based on normal probability theory. In contrast, confidence intervals based on the profile likelihoods provide a non-parametric alternative. In most instances, there will be close agreement between the 2 methods. In cases where they do not agree, Lothar and Skalski, 1996, proposed that the profile likelihood confidence intervals should be used. The theory behind the profile likelihood confidence intervals and the method for calculating them can be in Lothar and Skalski, 1996. SURPH3 allows the user to calculate 90%, 95%, and 99% profile likelihood confidence intervals for the CJS survival parameters and the overall survival as shown here. Once the estimation is complete, a corresponding profile likelihood report is available. Here you can see the 95% confidence intervals have been estimated and the report is available. If you want to re-estimate estimates that are already calculated with a different optimizer, for example, simply double-click on, in this case, estimate 95% interval. intervals. The previous estimates will be deleted and replaced with newer estimates. An unfortunate aspect of profile likelihood estimation in SURPH is that the validity of the results is somewhat optimizer dependent, especially when estimating the confidence interval of the function of parameters, for example, overall S. The estimates shown were calculated using the Fletch optimizer. The estimates here were produced using the direction set Powell's optimizer. Notice that the estimates agree except in the case of the overall S parameter, the product of the other survival probabilities. For this reason, SURPH-3 provides a profile likelihood diagnostic plot. Here we can see the diagnostic plot for the Fletch optimizer. As can be seen here, there are controls in the lower left to select the desired population parameter and confidence interval CI to view. The two vertical red lines indicate the upper and lower boundary of the interval. The horizontal red line indicates the target likelihood ratio corresponding to the desired confidence interval. The blue hatch marks correspond to the values that the profile likelihood estimation algorithm uses to search for the boundary values. As the search algorithm gets close to the desired likelihood ratio value, the step size gets smaller, which is why the points are closer together near the boundary values. Here you can see the points trace out a smooth curve on both sides of the boundaries. Compare this to here, where there's a lot of noise in the plots around the boundaries. This would indicate the estimates from the direction set optimizer should be used instead of the estimates for the Fletch optimizer. Experience seems to indicate that while Fletch is the best optimizer for estimating model parameters, the direction set optimizer seems preferable for estimating the profile likelihood confidence intervals. It is recommended that profile likelihood diagnostic plot be examined before using the estimated profile likelihood confidence intervals. This has been lesson 2 on using Program SURPH, in which we covered loading in your data with the various data menus, what the various data menus look like, and their function. Future videos in this series will cover creating your models and estimating your results, as well as hints and tips on getting the most out of the program. Please note that if for any reason you're having trouble with Program SURPH and these videos are not sufficient to answering your questions, you can find the user manual at cbr.washington.edu/analysis/apps/surph. The PDF manual is there, and you can either load it into a web browser or you can download it and view in Adobe. If you're using Program SURPH and you have any questions or comments on the same page, you may give us feedback via our user satisfaction survey. We would greatly appreciate any feedback you have in helping make future versions of this program to be more useful to our users. We hope that this video helps you get the most out of Program SURPH. Again, if you have any questions or comments in regard to Program SURPH, please fill out our survey as previously detailed. You can also contact Columbia Basin Research at web@cbr.washington.edu. Best of luck on your analyses, and thank you.